Welcome back, everyone. In this session, we're going to move in towards agglomerative hierarchical clustering. In the previous two lessons, we talked about what clustering is about, and also in the second lesson, we cover how to install a machine learning extension library. So let's move into hierarchical clustering, provided a reference in Wikipedia once again. In essence, this is really an agglomerative machine learning algorithm. How it works is that it's bottom up, and each observation starts in its own cluster, and pairs of clusters are merged as one moves up the actual hierarchy itself. Now, the second method is called divisive, and this one works from top down. So these are the two different ways that it actually create a hierarchical clustering. Now, in the divisive, all the observations start in one cluster, and then it splits, kind of like decision tree. The split are performed recursively as one moves down the actual hierarchy itself. Now, you may ask this question, okay, that's fine. You have a bottom-up, you have a top-down method. How does it actually do it? You'll be surprised that we've actually seen this before. It uses a distance matrix. If you look at this, hopefully, it will bear some resemblance to what we actually cover in the past. It uses Euclidean distance, which is a sum of all the difference, or the spread square, and then square root that. You also seen Manhattan. You also seen Mahalo Nobis. Okay, so in essence, we either use Euclidean or Manhattan. Most of the time, sometimes you do use the maximum distance. Now, the other thing that I do want to highlight is that the linkage criteria. The linkage criteria determines the distance between sets of observation. Well, I'm not too sure about you. For me, there's just far too much text to my liking. It just makes it really difficult to grasp this. So let me just come back to this. I'm just going to highlight a couple of links that please feel free to go and read. Again, they are still very filled with text. So let me just walk through these. I've listed down 5 different ways, okay, that people typically use for clustering methods. So that's when it comes to hierarchical clusterings. So let me just do some drawing. So when it comes to the single linkage method, it will take the shortest distance. So what we have here is the shortest distance between here and here. So let me just change the color to black. Shortest distance is essentially here to here. Okay, and when it comes to complete link, which takes the furthest distance, okay, the furthest distance here will be from here to here. All right, so that's really the second one. Okay, the average linkage method, it's really just take the average. Okay, so it's basically taking as an average of all pairwise distance. So it's a bit messy to draw, but you get what I mean. The centroid method, let's just pick a neutral color here, green. Okay, so the middle of this is this color. The middle of this is this. The middle of this could be here. So these are the so-called centroids. Okay, and what we're doing here is that we pick the one that's shortest. All right, so let's just choose back again. The distance between the two clusters is the distance between the two mean vectors. So in this case, is from here to here to here and to here again. And finally, let me just clean up here. So this is the Wards method is an iterative method. Okay, and it minimizes the total within cluster variance. So initially, what it does is actually it calculates within a cluster's variance. So it will look at this cluster, and that's the minimum variance, that's the cluster, and that's the cluster. After it's done that, the next thing is that, hey, between two clusters, which is the minimum. So when I look at this, this is smaller than this or this combined. So in the end, it will just choose to actually lump these two clusters together, okay, and leaving two clusters, which is this one and this one. and finally it comes to one big giant clusters. I hope that is useful. So let's move on from there. All right, so let's just start to write some codes. Right, we need to import our usual. So import numpy as np, import matplotlib as plt pyplot, and we want to plot this inline, and we also probably going to need pandas and also seaborn. Okay, right. The second thing is that let's make use of the scikit-learn data sets, and we have a samples generator that's called make blobs. Okay, so we will have x, y is equal to make blobs, and we have number of samples. Let's just set that to 600, and we have 5 centers, and the clusters. All right, that doesn't cluster standard deviation and is 0.6, and also random state is equal to 42. Okay. What's happened? Number of samples and centers, wrong spelling. Okay, and we'll just plot this so that we can actually visualize this. X and X, and makes the size at 10. All right, here you have it. You have 5 blobs. Okay, and so next thing that we want to do is make use of the SciPy, Scientific Python, and they actually have a built-in library called cluster and hierarchical, and then we're going to import ward, and we're going to need the dendrogram, and finally we're going to need the linkage as well. So NumPy, we set the printouts, the print options. We want to actually have the precision to 4 decimals, and right. All right. So we're going to calculate the distance, and this distance is going to calculated by the library that we import called linkage, and the method that we're going to use is ward. Now before I run that, so let's have a look at linkage and what is the actual so-called method. So in terms of the method that we use here is ward. If you look at it, there are actually a few of them that you can make use of. So you have single, you have complete, you have average, weighted, centroid, and finally ward should be in there as well. It even gives you the formula to go with it. How nice. And in essence, what basically is the single, the complete, the average, the centroid. There is actually another one called weighted, and finally wards. We already covered that. Okay, so let's run that. We're using ward. And the next thing that we want to do now is actually plot the dendrogram. Okay, now let's plot these out. Figure, and we're going to change the fixed size to 2510. This is quite a large one, so we need to actually put this to bracket, otherwise it's going to have an error. And I'm going to set this title and call it hierarchical clustering, then dendrogram. And the X label, I'm going to call this index, and the Y label, we're going to call it wards, distance. So I'll plot the dendrogram using the distance that's calculated, and we're gonna rotate the leaf. Let's go to 90 degrees. This is rotating the x-axis, the leaf. Font size is equal to 9. Might be still too big, but let's try it out. Let's plot that out and see. Okay, so here you have it. Yes, the font is still too big, so let's just shrink it down to, let's just 4 and see if we can actually still see this. Whoop, chop that off. 4. Anyway, you see what I mean? You can actually continue to play with this. Eventually you will come to a better font size. So what we have now is that you have the Y label is the words distance, and you have the X is actually the index itself, and this is really what you call a dendrogram. Okay, the alternative is that you can actually do this. Instead of plotting it that way, you can actually plot this and change your orientation to left. Totally up to you, and we're going to leave the rotation as that and leave font size as that as well. So this is, notice that it goes this way, and once you can actually turn it the other way as well. So there are many ways that you can actually plot this, so it's totally up to you how you actually want to actually display yours. So that's really very quickly how you actually make use of the dendrogram and also calculating the distance. We make use of a couple of libraries here. We make use of SciPy. Within SciPy we have word, dendrogram, and linkage. We use the linkage to actually calculate the distance between all of these. Of course, the method is not so straightforward. It uses the ANOVA method, and then after that we use the dendrogram visualization that is built into the SciPy. And that's really pretty much the end of this lesson. What I'd like you to do is actually change the centers. Instead of 5, try changing it down to 3 and see whether the actual dendrogram can actually do likewise or not. And what you can see here is one thing that you do observe. Now, although we have 5 blobs, we have substantially more what you would call leaf. And the question is, why? Well, the point is this. This is unsupervised clustering method. So it's an unsupervised machine learning method. It does not know how minute in terms of the granular details you should go down to. So at the end of these leaf, it stands alone by itself. You can of course truncate it if you want to, but that will be in our next lesson. But what we want to actually look at in terms of the intuition here is that at the 175 distance, that's 2. At the 125, there's 1, 2, 3. And typically what people say is that you cut it in order to actually change it to basically define the number of so-called blobs or the number of clusters. So let me just illustrate here is that if you actually cut it, let's just say at a distance of 25, what would you have? You will have 1, 2, 3, 4, 5 clusters. So that's the basic idea here in terms of, well, how you can actually make use of hierarchical dendrogram. And the machine learning algorithm or the clustering algorithm does not know when to stop. So this is where you actually do need to apply some sort of common sense to actually look at the cluster itself and learn how to play with it. But there isn't actually one so simple, straightforward method here to actually help you out. And if you cut it here, what you see is actually there's 1, 2, 3. So as an exercise, I'd like you to play around with this. Let me just close that off. Play around with this. To begin with, change the clusters to 3 and then change it to 10. And also vary the standard deviation to 0.1 and also down up to 1. And see if the actual hierarchical clustering, or HC for short, can actually pick up all of these It should be able to. It has been it is capable of doing that. So the essence of this is I want you to pause the video now, play around with it, and when you come back, I'll summarize the lesson. Alright, welcome back. I hope you actually given that a try and find the exercise helpful in terms of solidifying what you've learned here. What we've gone through in terms of this lesson really is understanding agglomerative hierarchical clustering. We focus on the bottom-up method rather than the divisive method. And we cover the few ways that you can actually perform in terms of the linkage between the actual so-called clusters itself. We walk through all of them and we write some codes, draw 5 blobs, and basically calculate the distance and then plot out the dendrogram itself. And in the next lesson, what we're going to do is that we're going to walk through how you can actually truncate the dendrogram itself, both writing in code and also the so-called intuition of doing so. So thank you for watching. I look forward to seeing you in the next lesson.